Right now, as you listen to this, billions of dollars of the global economy are routing through code written by people who, well, they probably retired a decade ago.
Oh, absolutely, yeah.
I mean, it's running our supply chains, our banking networks, our healthcare systems. And the scariest part, the people maintaining that code today are like utterly terrified to delete a single line of it.
Terrified is the right word.
Right. So picture a Tuesday morning where you are handed the keys to one of these ancient mission-critical code bases. The original architect left, 18 months ago.
hmm
The documentation points to systems that were literally decommissioned in 2021.
Which is incredibly common, by the way.
Yeah, exactly.
Yeah.
But this beast is in production. It's processing transactions. It is the financial heartbeat of your company. You make one wrong move or you misunderstand one bizarre function, and revenue just stops dead.
It is a genuinely terrifying position to be in. Yet it is the baseline reality for, well, the vast majority of staff engineers out there today.
Right.
Our industry is just so obsessed with celebrating greenfield projects,
Oh.
the pristine blank slates built completely from scratch.
Oh, totally.
But modernization isn't just some fun tech initiative. It is a fundamental business survival story. When a team cannot safely update its systems, the consequences don't just add up, they compound exponentially.
Yeah.
We see maintenance costs devouring like 70 to 80% of IT budgets.
Wait, 80%?
Yeah, up to 80%. And we see critical security vulnerabilities because the software relies on these unsupported, decaying runtimes. And ultimately, we see complete organizational paralysis because a 15-year-old monolith fundamentally cannot integrate with modern cloud services.
So today, our mission for this deep dive is to explore this high-stakes world of legacy code modernization. We are looking at how teams can safely navigate, refactor, and migrate massive systems that are actively making money, blending deep human insight with cutting-edge AI.
It's going to be a fascinating one.
I think so, too. We are pulling from an incredible stack of sources today. We've got Sudhanshu Mishra's Pragmatic Guide to Agentic Workflows, Prasad Bond's Deep Tech Analysis on the Load-Bearing Human, a really comprehensive modernization playbook from SourceGraph, Architectural Migration Insights from Shift Asia, and this is my favorite part, some incredibly raw, unfiltered realities from a viral Reddit thread on software architecture.
And what really stands out across all these sources is this complete rejection of the polished corporate narrative.
Oh, for sure.
If you read vendor PR, modernization sounds like a seamless lift and shift into the future. It sounds so clinical. But these materials, they bypass all that fluff to expose the structural flaws embedded in organizational psychology and legacy tech. They treat software not just as syntax, but as a complex social system.
Yeah, we are definitely keeping it grounded in reality today. To set the tone, there is a quote in Prasad Bond's materials that just perfectly captures the daily friction a staff engineer faces. It is a corporate punchline that hits almost too close to home. It goes, "I survived another meeting that should have been a database query today."
That phrase alone exposes the entire administrative bloat surrounding legacy systems.
It really does.
Right. Because when your underlying architecture is so fragile or so opaque that you cannot simply query it to understand its state, human meetings become the substitute for technology.
You're just replacing automated reporting with human consensus.
Exactly, which bleeds time and capital. And this points directly to the first major hurdle of modernization. Before we fix anything, we have to understand what we are actually looking at. And the core issue is almost never just bad code.
Well, let's talk about that greenfield illusion for a second.
Yeah.
You scroll through social media and you see someone claiming they, built an entire application over the weekend using AI.
Right, the weekend warriors.
Yeah. The repository is pristine. There are no inherited dependencies. Nobody is carrying a pager waiting for the database to lock up at 3 a.m. It is just this dopamine-rich sprint. But in the enterprise world, your day usually starts with a cryptic Slack message saying, payments are behaving weird, can you look?
The data has illuminated this divide for decades, honestly. Barry Boehm documented way back in 1981 that maintenance consumes the dominant share of software lifecycle costs.
1981.
Yeah. And Dave Farley's modern work on software engineering reinforces that maintenance is not a failure mode of software. It is the default mode for any system that actually survives its launch. The SourceGraph material cites a Krugel study showing developers spend only 11 to 30% of their time actually fixing technical debt.
And what's the rest of the time?
Well, the shocking part is that half of that remaining time is spent just reading the code, desperately trying to comprehend it.
Okay, stop right there because that statistic is staggering. Half their time just reading. So the bottleneck isn't typing speed or compiler times. The bottleneck is pure comprehension.
Precisely. And this is where Prasad Banda introduces this brilliant concept of the load-bearing human.
I see.
Imagine a board of directors demanding an automated, frictionless cloud migration. They assume the software is just a set of logical instructions that can be perfectly translated, but on the engineering floor, the actual blocker to migrating a 1998 COBOL stack isn't the proprietary language. The syntax is solvable.
Right, a machine can read syntax.
Exactly. The real barrier is the undocumented business logic. Enterprise software relies on humans who quietly carry risk across boundaries the code cannot cross.
So we are talking about like Dave in accounting or that one veteran engineer who knows why a specific routing script behaves the way it does.
Yes, these load-bearing humans hold the tribal knowledge. They know that a specific, really ugly piece of code was written to handle a vendor's API that mysteriously fails every leap year.
I want to try an analogy here because this is fascinating. Treating a legacy code base as just lines of text to be translated, well, it seems like looking at an old fence in the middle of a field and deciding to tear it down simply because the wood is rotting.
That's a great way to put it.
Right, like you can automate the demolition. But if you do not ask why the fence was built in the first place, you might realize too late that it was actually keeping wolves out. You cannot just evaluate the nails in the planks. You have to understand the history of the field.
That is a brilliant framing. An automated migration tool maps the structure of the fence perfectly. It can build you a brand new fence out of carbon fiber, but it strips away the unwritten business value, the human context that placed the fence in that exact geographical location.
So if an engineering team just accepts the output of an AI migration tool without rigorous contextual review,
They domesticate the output. That's what happens. They merge code they don't truly understand because rejecting the AI's work takes too much time and too much political capital. So the system quietly degrades. They tear down the old fence, build a shiny new one in the wrong spot, and suddenly the wolves are in the financial system.
oh man, that place is just a crushing burden on the staff engineers. Sudhanshu Mishra breaks down this daily dilemma beautifully in his piece. A staff engineer is ordered to change a load-bearing component without disrupting the active revenue stream. But at the same time, they are still handling daily maintenance and triaging P1 incidents. How do you even balance long-term modernization with the chaos of a live outage?
The cognitive load is immense. Just imagine the core authentication service goes down. The engineers diving into a code base they might not have even written, trying to trace an error, while executives are demanding an estimated time of recovery every 5 minutes. Unbelievably so. The job of finding the technical flaw and the job of managing stakeholder panic compete directly for the engineer's finite attention. Mishra suggests mitigating this through a centaur model.
The centaur model, like blending human and machine intelligence.
Yeah, exactly. During an incident, the human should not be tracing logs manually. The human contributes high-level judgment, business prioritization, and stakeholder communication. The AI agent, on the other hand, contributes extreme breadth and speed.
So the AI is doing the grunt work.
Right. It can ingest an error signature, trace it through thousands of commits across 50 repositories, and instantly generate a narrowed set of candidate hypotheses for the human to review.
But I have to challenge the limits of that AI speed for a second. The AI can highlight plausible technical hypotheses based on commit history. But as we just established with the fence analogy, the syntax does not tell the whole story.
Very true.
If the biggest danger is accidentally deleting a hidden business rule, an AI tracing error logs won't really help us discover those implicit rules before we start tearing down the fence. So how do we find the wolves before we demolish the wood?
Well, you definitely cannot wait for the system to crash to discover what was load-bearing. Prasad Band offers a highly tactical approach for this, which he calls the 48-hour validation.
Okay, let's get into this.
It is beautifully simple. You do not start by reading the code. You start by running a git history script against the oldest repository, something like a git log format command. You extract the names of the most frequent authors over the last decade.
So you're using version control to map the human organization, not the software.
Exactly. You are finding those load-bearing humans, and once you have those names, the next step is critical, and it has absolutely nothing to do with programming.
What is it?
You schedule a 15-minute coffee with the top 2 names on that list. You look them in the eye and ask one specific question. What breaks if this system is turned off tomorrow?
That is fascinating. You don't ask them for a code review. You ask them for the catastrophe scenario. You are extracting the domain context, like the historical trauma of the system, before you even touch the architecture.
And this bridges the divide between technical debt and domain knowledge. The viral Reddit thread on software architecture that we reviewed highlights this trap perfectly. A team makes a change that passes every single technical check. The code is modern, the tests are green, the deployment is flawless.
Sounds like a success.
It does. But the system immediately starts producing catastrophic business outcomes because they deleted a rule they thought was just technical debt.
Yeah, someone in that Reddit thread dropped a line that had me laughing out loud, but it is deeply terrifying. They said, "It's not a requirement, it's not a design rule, it is a load-bearing class definition."
That perfectly captures the anxiety of legacy systems.
Yeah.
And how do you determine if an ugly, convoluted piece of code is just obsolete junk from 10 years ago,
Yeah.
or if it is a structural pillar holding up the entire enterprise?
Well, the poster in that thread actually provided a fantastic triage methodology. They listed 5 specific questions a team must ask to differentiate between obsolete code and hidden business rules. Let's break these down because they really reframe how we look at code.
To it.
The first question is, what business decision does this component encode? Notice it is not asking what database it queries. It asks what decision it makes.
That distinction is paramount. A component might exist solely to decide if a customer in a specific region gets a promotional discount. Once you know the decision, you move to the second question. Who depends on that decision downstream?
Right.
This requires mapping business capabilities to software components. The Reddit thread cited a scenario where developers found a messy data aggregator. It looked like pure technical debt. But upon mapping it, they realized 6 different downstream financial reporting processes depended on its exact, quirky output format. Touching it blindly would have corrupted the quarterly financial reports.
Wow. So the third question challenges the history of the decision. Is the decision still valid or just historically preserved? I imagine a lot of code exists to work around bugs in third-party services that literally went out of business 8 years ago.
Oh, a staggering amount of enterprise code is just scar tissue from past vendor failures.
Scar tissue, that's a great term for it. And the fourth question follows that thread. Is this logic protecting an edge case?
Yes.
And the fifth question is perhaps the most critical one for modernization teams. Are our tests validating the business intent, or are they only validating the current implementation?
And that fundamentally changes how we view testing.
Right. We are always taught that unit tests are our absolute safety net. But if we skip the coffee meeting with the load-bearing human and we ignore these 5 questions, aren't our tests just enshrining old mistakes?
Just exactly.
Like if a system has a bizarre rounding error introduced in 2014 and we write a test ensuring that rounding error happens perfectly every single time, we haven't modernized. We've just automated a ghost.
Modernization teams underestimate this trap constantly. Tests prove what the system does today. They prove your refactored code behaves identically to the legacy code, bug for bug.
Right.
But a test cannot tell you if that behavior still deserves to exist in the business model. Only human judgment can validate the intent. If you merely test the implementation, you preserve history without proving its validity.
Okay, so we run the Git script, we buy the coffee, we interrogate the load-bearing humans to map the hidden business constraints. We now know the history of the fence. Now what? We are still standing in front of a colossal, aging technology estate that desperately needs to be updated. How do we structure this operation so we don't just drown in complexity?
This is where the SourceGraph Modernization Playbook provides massive value. You need a structured framework to evaluate the estate. But step 1 is brutally simple. You cannot modernize what you cannot find.
Makes sense.
So you have to build a comprehensive inventory of your dependencies.
And the playbook is adamant about this. Do not rely on human memory and absolutely do not trust stale architecture diagrams. You need a template that maps the repositories, the microservices, the shared libraries, the third-party APIs, the batch jobs, and all the cross-service connection points.
Furthermore, you have to validate this inventory dynamically.
What do you mean by dynamically?
Well, you cannot just read static code to see what talks to what. You have to observe the live runtime environment, what is actually making network calls in production. Once you have a validated map of the estate, you can apply a prioritization framework. And the industry standard here is the 7 Rs framework.
Let's dive deep into these 7 Rs. I want to move away from just listing them and actually apply them to a real scenario.
Good idea.
So imagine we are modernizing a 20-year-old logistics and shipping company. We've got hundreds of systems. The first 2 Rs are the low-effort plays, retain and retire.
Let's look at retain first. Retain means you do absolutely nothing to the code. You freeze it, document it, and leave it running. In your logistics company, maybe there is a small internal tool that calculates the volume of standard shipping containers.
Right, the math doesn't change.
Exactly. The math of a rectangular box hasn't changed in 20 years. The tool is stable, it requires zero maintenance, and it serves its purpose. Retain it. Do not waste engineering cycles rewriting it in Rust just to feel modern.
But the second one, retire, that sounds like the ultimate developer fantasy, just
Yeah.
hitting the delete key.
Retiring a system is the highest value decision an engineering leader can make. Cutting scope is infinitely cheaper than rewriting code.
So true.
Let's say your logistics company built a custom employee portal for tracking vacation days back in 2005. Today, HR uses Workday, but the old portal is still running on a server somewhere, consuming resources and posing a security risk, just because nobody officially turned it off. Finding that duplicated or orphaned functionality and terminating it is a massive immediate win.
I love the idea of just unplugging the ghost servers. Okay, now let's look at the middle tier effort. Rehost, replatform, and repurchase. How do we differentiate these?
So rehost is your classic lift and shift. You take the application exactly as it is and move it to a new environment. Suppose your logistics company has a mandate to exit a physical data center in Chicago by the end of the year.
Okay.
You take a monolithic routing application running on bare metal, and you drop it into a virtual machine in AWS. You change zero code. It's pure infrastructure play to solve a hosting problem.
But replatforming implies tweaking the engine a bit while you move it, right?
Yes, replatforming is medium effort. You are moving to the cloud, but you want to extract some immediate operational benefits without rewriting the business logic. Instead of just migrating the old Oracle database to a cloud VM, you migrate the data to a fully managed cloud database service like Amazon RDS. Or you take the application code and wrap it in a Docker container so it can run on Kubernetes. You're changing the runtime environment, not the core logic.
Got it. And repurchase is admitting defeat on building things yourself.
Well, it is admitting where your business value actually lies. Repurchase means abandoning your custom legacy system and buying a commercial SaaS product. If our logistics company is running a custom-built CRM from 2010 to track sales leads, they should throw it away and buy Salesforce.
Right, because you're a shipping company, not a CRM company.
Exactly. You only build custom software for capabilities that differentiate your business in the market. Nobody buys your shipping services because you have a cool, custom-built CRM.
Which brings us to the heavy hitters, the systems that actually differentiate the business. Refactor and re-architect or rebuild. These are the dangerous ones.
Very dangerous. Refactor is medium to high effort. This is where you physically restructure the code to pay down technical debt, improve performance, or patch deep security flaws. The critical constraint here is that the external behavior, the inputs and outputs, must remain identical.
Give me an example in our logistics company.
Imagine the core pricing engine. The architecture is sound, but over 20 years, developers have bolted on so many quick fixes that adding a new pricing tier takes 6 months. You refactor the internals to clean up the friction, but the system still accepts a weight and outputs a price just like it did yesterday.
And re-architect or rebuild is the nuclear option.
It is the highest effort, highest risk choice. You tear it down to the studs and design a fundamentally new architecture. You only choose this when the legacy architecture is the actual bottleneck preventing business growth.
So like if it simply can't scale.
Right. If your legacy logistics system can only process batches of data overnight, but your new major client demands real-time, event-driven tracking, you cannot refactor your way out of that. You have to rebuild.
But how do teams actually decide which system gets which R? SourceGraph recommends a risk versus impact analysis using a 2x2 matrix. I really like this part.
It is an excellent visual tool. You plot every application in your inventory. The y-axis is business criticality, how much revenue flows through it, what is the regulatory or compliance exposure, how customer-facing is it.
Okay, and the x-axis?
The x-axis is technical condition. What is the test coverage? Is the runtime framework still supported by the creator? How observable is the application in production?
So if an application is low criticality and terrible technical condition, you retire it. If it is high criticality and great technical condition, you retain it. But the danger zone is high business criticality, coupled with terrible technical condition. That is where you have to refactor or rebuild.
And that danger zone is where staff engineers earn their paychecks.
Let's walk right into that danger zone. We have our inventory, we've mapped the business rules, we've plotted our systems. Now comes the terrifying execution phase. We have to refactor a high-risk, mission-critical monolith. How do we do this without accidentally bringing down the company?
The answer lies in establishing an impenetrable safety net before you touch a single line of business logic. Michael Feathers, a pioneer in legacy code, coined the concept of characterization tests. He famously described refactoring without them as being akin to rearranging dynamite.
Rearranging dynamite is such a visceral image, but I want to get into the nuts and bolts here. A characterization test sounds different from the standard unit test developers write every day.
They serve completely different masters. A standard unit test asserts what the code should do based on the requirements. A characterization test is completely agnostic to requirements.
Oh, really?
Yes, it simply pins down exactly what the code currently does in reality, including all of its undocumented quirks, bugs, and bizarre side effects.
Yeah.
You were taking a perfect mold of the current reality.
The outline provides a specific checklist for creating these tests. Step 1 is picking a very specific slice of the legacy system. Step 2 is running that slice with realistic inputs. Step 3 is capturing the exact outputs. But here is the mechanical problem. In a 15-year-old monolith, an output isn't always a clean return value on a screen. Often the output is a side effect. It writes to a database, or it fires off a message to an asynchronous queue. How do you capture that?
That is the crux of the engineering challenge right there. You cannot run these tests in a live production database because you would corrupt real data.
Right.
You have to isolate the slice. This involves setting up proxy servers to intercept outbound API calls or using database snapshotting. You run a transaction, capture the exact state change in a localized mock database, and record the exact payload sent to the message queue.
So you're trapping the system in a controlled box and recording everything it touches. Step 4 is turning those captures into golden file tests. If your new refactored code changes that captured output by even a single byte, the test fails. And step 5 is adding property-based tests for invariance. I want to unpack invariance because it is kind of a dense term.
An invariant is a condition that must remain true throughout the execution of a program, regardless of the inputs. Let's apply it to a banking application. An invariant property of a fund transfer function is that money cannot be created or destroyed. It can only change locations.
So you don't write a test that says, if I transfer $10 from account A to account B has $10.
Exactly. You do not test specific values. You write a property-based test that generates 10,000 random, highly complex transactions. The test asserts a single invariant. The sum of all balances across all accounts before the execution must perfectly equal the sum of all balances after the execution.
That is brilliant.
If your refactored code loses a single penny or generates a phantom cent due to a rounding error, the invariant test catches it immediately.
Once that massive safety net is strung beneath us, we still have to swap the old code for the new code. We cannot just flip a switch on a Friday night and pray it works on Monday morning.
Definitely not.
This brings us to a concept from Martin Fowler, the strangler fig pattern. We all know the botanical metaphor: a vine grows over an old tree, eventually replacing it as the host guys. In software, this means building new features alongside the legacy system. But setting up that routing facade when you have a tangled, stateful monolith seems like a nightmare. Let's talk about how you actually route that traffic safely.
The mechanics of the strangler fig routing are highly complex. You place a facade like a traffic proxy in front of both the legacy system and the new modern system. When a request comes in, the facade determines where to send it. The power here is the dial. You can configure the facade to route 99% of traffic to the legacy system and 1% of traffic to the new system.
But what about state? Like if a user starts a session on the old system and their next click is routed to the new system, they're going to get logged out or lose their shopping cart.
This is why the routing must be incredibly sophisticated. You have to implement sticky sessions at the facade layer, ensuring a user's entire journey stays on one path. Or you have to implement bidirectional data syncing between the legacy database and the modern database so both systems share a unified state in real time.
That sounds really hard.
It requires immense engineering discipline, but the payoff is total reversibility. If that 1% of traffic hits a catastrophic error on the new system, you do not roll back a massive deployment. You just turn the dial on the facade back to 100% legacy traffic. It takes Milliseconds.
Over time, you watch the metrics. You see the API calls to the old system drop from 400 to 100, then to 0. The new vine has strangled the old tree, and you can safely delete the legacy code.
Beautiful, isn't it?
It is, but I see a human behavioral trap here. Couldn't an engineering team tell leadership they are doing a strangler fig migration, but in reality they just go dark for a year, building a massive parallel system without routing any real traffic until the very end?
You have identified the most pervasive anti-pattern in modernization.
Wait, really? People do that?
Teams do this constantly because incremental delivery is painful. It requires maintaining two systems simultaneously. But a secret parallel build is not a strangler fig. It is a delayed Big Bang rewrite wearing a disguise.
A disguise, I like that.
The absolute law of the strangler fig pattern requires shipping a thin slice of functionality to production, routing real human traffic to it, and learning from the failures incrementally. If you are not testing the new path in the real world, you are just accumulating massive risk in the dark.
Doing all of this, manually running the Git scripts, mapping the 7Rs, writing the golden file tests, configuring the stateful routing facades, it is grueling. For a massive enterprise, this could take half a decade.
Easily.
This is where we finally bring AI agents into the narrative,
Right.
but we have to be extremely precise. These agents are not magic wands that replace engineers. They are force multipliers for code comprehension and scale.
The insights from Sudhanshu Mishra's piece on agentic workflows perfectly illustrate this transformation. Think back to the administrative bloat we discussed earlier. You need to understand a massive, unfamiliar code base to draft a migration plan. Historically, your only option was to bother busy veteran engineers disrupting their workflow to gather asynchronous context.
Right, you are pinging Dave in accounting, and he is irritated because he's trying to restore a down database.
But an agentic workflow changes the shape of the interaction entirely. Using a tool like Claude Code, you provide a rough, natural language intent. You say, I need to understand the payment flow in this repository to identify high-risk dependencies and draft a strangler fig routing plan.
And AI just does it.
The AI agent reads the repository, traverses the file tree, evaluates the test coverage, and generates a structured, highly detailed draft.
That fundamentally changes the human interaction. When you finally go to Dave, you are not asking him to whiteboard the architecture from memory. You hand him the AI-generated draft and say, here is the baseline, what is factually incorrect or missing from this. You shift the human burden from generation to correction.
It accelerates comprehension exponentially. And modern tools delineate between deterministic search and deep search. Deterministic search is exact pattern matching. If an auditor demands proof that every instance of a deprecated security library has been removed across 5,000 repositories, a deterministic code search gives you an exact mathematical answer.
But deep search is semantic, right?
Yes, deep search uses agentic logic. You can ask a natural language question like, how does user authentication propagate through these 3 legacy microservices? The agent understands the semantic meaning of authentication and traces the data flow, even if the variables are named inconsistently across the services.
And once we comprehend the code, we can use these agents for cross-repository refactoring. Tools like SourceGraph, Open Rewrite, or CodeMod allow teams to execute massive mechanical changes. If we need to upgrade a core networking library or translate a specific isolated COBOL batch job into Java, we define the transformation rules and the agent applies it across thousands of repositories in hours.
But unleashing an agent across 1,000 repositories requires ironclad guardrails. You can't just let it run wild. This is executed via agent constitution files like claude.md or agents.md, which live directly in the root of the repository.
What does a constitution file actually look like structurally?
It is a set of standing operational orders for the AI. You encode rules such as you may not modify any file in the legacy billing directory, or any structural change to an API endpoint must be accompanied by a property-based test, and you must run the test suite and achieve a passing result before marking the task complete.
Oh, wow. So you don't have to tell it every time.
Exactly. You do not rely on a human remembering to type those constraints into a prompt every single time. The constraints are structural to the workspace.
Even with constitution files and deep search, we have to confront the ultimate limitation of AI in this space. The AI can parse syntax flawlessly, but it is entirely blind to the human history of the organization.
This is the critical reality check from our deep tech sources. Agents are incredibly powerful hypothesis engines. They can tell you exactly how a legacy system executes its logic today, but they cannot tell you why that logic exists or how the system should behave in the future.
Right.
They suffer immensely when the context lives outside the version control system. If a bizarre piece of code exists to satisfy an unwritten legal compliance agreement or some corporate political compromise from 2018, the AI has no visibility into that.
Which brings us to the final brilliant punchline from the Reddit thread we sourced. A developer perfectly summarized this limitation by saying, "Thanks, Claude. Now review PR TAC 14376."
It is a sobering reminder. The AI can generate the refactored code in seconds, but a human engineer still has to review it, understand it, and take the ultimate legal, financial, and operational responsibility for merging it into a live production environment. You cannot outsource accountability.
You really can't. Let's synthesize all of this because we have covered a massive amount of ground. If you are a staff engineer staring down a terrifying million-line legacy estate today, your first step is not to open an IDE and start writing new code. Your first step is discovery. You run the Git script, you identify the load-bearing humans, and you ask the critical questions to map the hidden business constraints.
And once the context is extracted, you use the 7Rs framework to categorize and prioritize the estate, aggressively retiring what you can to cut scope.
Yes, turn off those ghost servers.
When you must refactor, you rely on characterization tests and invariants to capture the current quirks of the system, and you utilize the strangler fig pattern to safely route stateful traffic and learn incrementally. You leverage AI agents heavily to compress the time spent on code comprehension and cross-repo syntax changes, but you never bypass the load-bearing human who understands the why.
This has been an incredibly illuminating journey into the real trenches of enterprise software. But before we sign off, I want to pivot and leave you with a provocative thought that builds on everything we've discussed. We've spent this entire deep dive analyzing how to safely untangle the legacy code of the past, the monolithic architectures and undocumented scripts from 20 years ago.
But look at the sheer volume of AI-generated code that development teams are rapidly accepting into their code bases today, often without deep contextual review.
It raises a fascinating and somewhat chilling question. Are we currently writing the most incomprehensible, context-free legacy code in the history of software? When the next generation of engineers attempts a modernization project in 10 years, will the load-bearing human simply be the one person left in the organization who remembers what prompt was used to generate the system?
That is a very real possibility.
That is something to seriously consider the next time you hit tab to accept an autocomplete suggestion. Remember, when you are looking at an ancient code base, you are not just looking at syntax, you are looking at the sociological history of a company. Do not tear down the fence until you know exactly why it was built. Thank you so much for taking this deep dive with us today. We will catch you on the next one.